Some practice problems are listed here in this video, and also can be found in the note shells, the video shells in Blackboard Learn. The solutions are here. These are just second order linear constant coefficients, but some extra practice for you. One of the things we talked about in class was the Fibonacci sequence that has this particular form here, and with these initial conditions, and we wrote out what the Fibonacci sequence looks like for the first several terms. 1 and 1 are the initial conditions, and then each term thereafter is a sum of the previous two. So these are the kinds of terms we get there. Well, to solve it formally, then we use the characteristic equation. R squared is equal to R plus 1 from the coefficients of the terms in the recurrence relation, and that has this solution here, 1 plus or minus the square root of 5 over 2, which would mean that the recurrence relation without the initial conditions has this general solution for arbitrary constants alpha and beta. If we apply the initial conditions, just doing the algebra on it, we get 1 over the square root of 5 and minus 1 over the square root of 5 for the coefficients alpha and beta for those constants there, and therefore the Fibonacci sequence has this closed form, which is kind of remarkable because it has these radical 5s in it, and yet for every positive integer that would simplify to an integer itself, as in the sequence terms up here. But there it is. Fibonacci sequence is a nice one to see. It's worth seeing that. This is part of our discussion of recurrence relations. So having looked at some homogeneous ones of various orders, including up to order 3, we've done some of those problems in the web work and in class. Now we want to look at the non-homogeneous case. And so we'll start off by recalling what the homogeneous case looks like for the linear first order with constant coefficients. So the simple case of the first order should help us understand some general principles here. In this particular example 1 that I've got here, an is equal to 4an minus 1, first order linear. And the general solution for that then would have the form of an is equal to some constant, I'll just call it alpha like we often do, times 4 to the n. That's kind of a funny looking 4, but that's what that is, 4 to the n there. So there's the general solution, and this is an a right here, like so. And we know that when we're given a 0, that would say that that constant will be a 0, the initial condition. In this case, it doesn't always work out that way. That is to say, for higher order, it won't work that way, and for the non-homogeneous, it won't either. Here's our first non-homogeneous one we'll consider with the 6 here, and I might point out the contrast between this and the one before. We could have written the one before in this form here, putting all of the terms of the sequence on one side of the equation and anything else on the right hand side. And the 0 here is the indicator that it's homogeneous. So in this one right here, if we did the same thing, we'd have an minus 4, an minus 1 is equal to 6. So what we're trying to do is find out a solution of that. We do know how to do it when it has a 0 there, and that's going to figure into this. But in particular, we want to figure out what will happen if we have something like a 6 or another constant there. What sort of a sequence would give us a solution that has a constant after we take one term in the sequence and subtract 4 times the previous term in the sequence. And that's really what this is saying. Take a term in the sequence, subtract 4 times the immediate preceding one, and we get a 6. Every time we do that, every time we look in the sequence. When you have a constant here, as we have the 6, one thing that we might try is an actual constant sequence. So we might try a sequence of the form. So we'll try constant sequence, which means we might have a sequence of the form like A0 is some constant, let's just call it D. A1 is the same constant, D. A2 is the same constant, D. So A sub n is equal to D no matter what the subscript is here. And if we try that into our equation here, then we would have an is D minus 4an minus 1 is minus 4d because it's constant is equal to 6, and that's a fairly simple equation to solve. That gives us d is equal to minus 2. So in fact, that's a d there. The sequence A sub n, and I'll put a little p up here for particular, which is constant, is a solution. I'll say a particular solution. And this equation that we got is equivalent to the original expression we'd have. In other words, if we substitute that in up here, we would have that minus 2 minus 4 times minus 2 is equal to 8 minus 2, which is indeed 6. Or if you use the original form up here, same thing. So that is a solution, that constant sequence. And what I want to convince you of now is how we can combine that with the solutions of the homogeneous equation to get the whole realm of solutions here. So the homogeneous equation solutions, I'm going to call an with an h. That's an h up there, and that's equal to alpha times 4 to the n, where alpha is an arbitrary constant, and these are the homogeneous version in part 1 solutions. Again, the h there as a superscript in parentheses, that's what that little thing is, an h. That's intended to indicate that we're talking about the solutions of the homogeneous. Well, the point of this little discussion here is if we solve, or if we take these two here and add them, we will get another solution of the non-homogeneous equation. In other words, if we take an superscript h, that's equal to 4an minus 1 with the superscript of h plus 6. Because these things here all solve the homogeneous, and there should be no 6 here. That should be 0 for the homogeneous. I'll get that plus 6 for the non-homogeneous. So if we take AP, that sub n, that is AP sub n minus 1 plus 6, because that particular sequence, in this case it's just a constant, but I'm trying to think about this in a little more general terms, that solves the non-homogeneous equation. Now what I want to do is add and get an superscript h plus a and superscript p is equal to, I forgot that 4 right there, you let me forget that, right? Okay, that 4 there is equal to 4 an minus 1 superscript h plus an minus 1 superscript p, adding these two terms here, this term here and this term here, and then finally we have the plus 6 like so. So this sequence made up of the sum of the previous two, call it a sub n, is equal to 4a sub n minus 1 plus 6. So that tells us that anything of the form a sub n equals a sub n h plus a sub n p, the homogeneous plus the particular solution of the non-homogeneous equation, is a solution of the non-homogeneous recurrence relation. In fact, that's all of them. I will show that a little later. Now, we have room here. Let's go ahead and do that. Suppose you have another one. If Bn also solves it, 2, like so, then let's just check this out and say, okay, what about Bn minus a sub n p, the particular one? Okay, Bn, or excuse me, a sub n p, the particular one, is the circled one up here, okay, the particular one we found, and this will work in a general way, not just in this particular equation. But if we put that into our original recurrence relation, an minus 4, an minus 1, that is to say, if we put this in there, we'd have Bn minus an p is equal to 4 times Bn minus 1 plus 6, because that's what Bn solves. Bn solves the this equation right here, and so does ANP. That would be 4an minus 1 superscript p plus 6. The 6's cancel, and we have that's 4 Bn minus 1 minus an minus 1 combined like so. In other words, the difference of any solution of 2 and the particular one we already identified solves the homogeneous equation. The nth term is 4 times the n minus 1 term. So that would say Bn minus 1 minus an minus 1p has to be a solution of the homogeneous, which is 4, excuse me, it is, yeah, alpha times 4 to the n. That is to say, Bn minus 1 has to be, Bn, get rid of those, Bn minus anp has to solve the homogeneous. That's the nth term in n minus first. So that's equal to alpha 4 to the n. So Bn is equal to alpha 4 to the n plus anp, and that is simply Bn is equal to one of the solutions of the homogeneous plus the particular solution. So let me summarize this real quickly and then we'll stop this one. That is to say, the solution of the non-homogeneous, all of them, are of the form of the homogeneous solutions, which have an arbitrary constant in them, and any single particular solution that gives you all of them. That's a pretty long video. We're going to stop there.